Yeah, hi everyone, welcome to PrepFusion. So in this video, we are going to see how to solve the problems related to setup time and hold time in digital circuits. Like usually you are comfortable with delay based problem, but when it comes to setup time, hold time, we struggle here, sir. Sir, just let me know some way that I would be able to solve problems related to setup time and hold time. So what's that way that we need to see? First, we need to understand the basic meaning of setup time and hold time. After that, I will develop a problem solving technique. Sir, here will you be giving me concept? No. We will just develop that problem solving technique that if you solve the particular question in this manner, then your answer will be matched. This is what we are going to learn, and surely you will be able to solve the questions that is coming in your gate examination. In future as well, if some question is coming from this particular topic, you will be able to solve it. But if you want to know the complete depth, if you want to know that, sir, from where all the concept came, then you can watch this particular video. STA by Himanshu Agrawal, you will type static timing analysis by Himanshu Agrawal. Complete video is there. You can see the number of views as well. This is loved by a lot of students. So complete in-depth explanation of setup time, hold time, that how in a particular circuitry setup time can create issue, how in a particular circuitry hold time can create a issue. So within 3 hours you will be able to understand it. And notes are also uploaded on the Telegram channel as well. But some people want very fast problem solving skills. So for them I am making this particular video. Okay. So let's get started and understand the basic meaning of setup time. First, forget about setup time or hold time. If this particular question I am giving you, that there is a T flip flop, okay, it is fed with the positive edge triggered it is a positive edge triggered flip flop, okay. So clock is positively edge triggered. Now what will be the output Q? Draw the waveform of output Q. Initially let's just assume that it is clear. Initially output is 0. So what will be your output Q? What you will say, sir, at the positive edge it will see the input. The scenario is that, sir, if T is equals to 1, then output will be toggling, and if T is equals to 0, then output will not toggle. You need to have a basic idea of digital circuits, then only you will be able to understand this video. It's not that, sir, I don't know digital circuit at all, can I study it? No, you need to have a basic idea of T flip flop, JK flip flop, then only you can understand it. So what I am assuming is that there is no setup time, there is no hold time. I am not studying about it. This is simple question is there, that this particular flip flop is there, and now we are asking a question that if this kind of clock is there and this kind of input is there, this is your T input, then what will be your output? How will your output look like? Then you will say that, sir, when the positive edge is coming, it will look at the input. What is the input? Input is 1. Since the input is 1, what will happen? Output will toggle. So from 0 to it will go to 1. From 0 to it will go to 1. Now again at the positive edge, again it will see the input. What is the input? Input is 1. That means it should again toggle. That means from 1 to 0 it will go. And it will toggle here and it will hold till the next clock edge. So again clock edge is coming. Again it will see the input. Again input is 1. That means again toggling would be there. Then again at the positive edge, again input is 1. Again toggling would be there. So this would be my ideal output. Considering there is no setup time, hold time, I don't even know what is setup time and hold time. So this is how your output will look like. 0, then toggling here, then toggling operation here again, then again toggling operation, and then again toggling operation. So this is how my output would look like. But when you design a particular flip-flopper, then they will have some setup time as well, and they will have some hold time as well. So let's just say setup time is 3 nanosecond and hold time is 2 nanosecond. So what is the meaning of this 3 nanosecond or 2 nanosecond? So now this clock edge, at this clock edge, he will see the input. Input is 1. So ideally he should toggle. But now what clock will say? Clock will say that, sir, the flop that you are using, that is having a setup time of 3 nanoseconds. So what I will do is that from this particular clock edge, let's just say this clock edge is occurring at t equals to 0 nanosecond. So from this clock edge, listen to me very carefully. From this clock edge, I will look back for 3 nanosecond. I will look back for 3 nanosecond. So at t equals to 0 nanosecond, what is the input? 1. He will look back for 3 nanoseconds. So from 0 to minus 3 nanosecond, input should be 1 only. The input should be stable. Is that understandable to you? What did I just say? What is the meaning of setup time? Setup time means that, sir, setup time is 3 nanosecond. So clock will say that, sir, yes, at the positive edge of this clock, at this particular edge, I am seeing the input 1. That means I am supposed to toggle. I will toggle only if your input is stable for the previous 3 nanosecond. Because your setup time is 3 nanosecond. That means your input should be stable for the previous 3 nanosecond. Is it stable for the previous 3 nanosecond? At 0 it is 1. Then at a minus 1 second it is 1. Minus 2 nanosecond it is 1. Minus 3 nanosecond it is 1 only. Yes, input is stable. For the previous 3 nanosecond it is stable. So this is the first condition the clock will say. Other condition the clock will say that, sir, yes, I am looking back as well, I will look ahead as well. How much I will look ahead? Equal to the hold time. So this clock edge will say that, yes, I am supposed to toggle, but I will only toggle if your input is stable for the next 2 seconds as well. That means in a complete window of 5 nanosecond, your input should be stable. If this condition is not matched, then output will be unpredictable. But here you can see that just as the clock has arrived, what is the meaning of setup? Setup means something that has to be stable back then, right? What is the meaning of setup? Setup means something has to be already stable. So when the clock edge is coming, the input should be already stable for the 3 nanosecond. And what is the meaning of hold? Hold means input should be holding its value for 2 more nanosecond. Is that clear to you or not? So when the clock edge is coming, setup time for 3 nanosecond it will look back. For 2 nanosecond it will look ahead. Slowly you will understand the meaning more. So here there is no issue. That means there is no setup violation. What is the word that we use? No setup violation. And there is no hold violation. There is no hold violation. That means here there is no issue. So it will be toggling from 0 to 1. It will be toggling. Let's just remove this. This was the ideal waveform, but let's make the actual waveform. So at this particular clock edge, at t equals to 0, it will be toggling. There is no issue. But now let's come here. Now someone will say that, sir, the time period is not constant. So forget about the time period. Like here the window I have made 7 seconds only, but this window is 10 nanosecond. So don't worry about that. I am just giving you the concept of setup time and hold time. Now at the next clock edge, what he will again say? That, sir, yes, I am supposed to toggle. I am supposed to toggle. But what is my condition? That my input, that is 1. At the clock edge, input is 1. But it should be stable for previous 3 nanosecond because setup time is 3 nanosecond. So it should be stable for previous 3 nanosecond. Is it stable for the previous 3 nanosecond? Just let me know one thing. Is it stable? At 7 nanosecond, this is your 7 nanosecond, right? At 7 nanosecond, you can see that input is 1. But previous 3 nanosecond means 7 minus 3. That means at 4 nanosecond, what do you see? The input is 0. At 5 nanosecond, what do you see? Input is 0. But the condition was from 4 nanosecond to 7 nanosecond, input should have been from 4 nanosecond to 7 nanosecond, input should have been 1. If the input was already set up, then he would say that, sir, yes, I will be toggling. But input is not set up, then he will say, sir, I don't know. Either it can toggle as well, it cannot toggle as well. Output will be unpredictable. You cannot predict the output. That means, yes, there is a setup violation now. So at this particular condition, at a 7 nanosecond, what do you see? At 7 nanosecond, there is a setup violation. Setup violation is there. Okay. Is there hold violation? Let's check. What is the condition of hold? Hold means that input should be held for 2 more nanosecond. Input should be held for 2 more nanosecond. That means for next 2 more nanosecond, input should be held. So from 7 to 9 nanosecond, input should be held. So 7 nanosecond 1, to 8 nanosecond 1, 9 nanosecond 1 only. So yes, there is no hold violation, but there is setup violation. So if one of the violation is there, then output will be unpredictable. Your target is to avoid both of the violation. That means this is your ideal condition, that setup violation should also be avoided and hold violation should also be avoided. But when I came here, when I came at this particular trigger, I saw that there is no hold violation. I am fine with that, but there is a setup violation. That means output will be unpredictable. Either it could be 1 or 0. Let's just say it is 1. Let's just assume it to be 1. We are not sure. Let's just assume it to be 1. But here there is a setup violation. Here there is setup violation is there. Okay. Let's go to this guy. What about setup time? He will say that, sir, my input should be set up for 3 nanosecond already. So at 17 nanosecond, I am seeing 1. But I need to go back. At 17 nanosecond, I can see that I am having input to be 1. But 3 nanosecond back. What is the meaning of 3 nanosecond back? 17 minus 3, 14. So till 14 nanosecond. That means from 14 nanosecond to 17 nanosecond. From 14 nanosecond to 17 nanosecond, input should be stable. Is it stable at 1? Absolutely, it is stable at 1. So from 14 to 17, input is stable. There is no setup violation. But what about the hold violation? What is the meaning of hold time? That means for next 2 nanosecond, input should be stable. So you are at 17. Next 2 nanosecond. That means till 19 nanosecond, input should be stable. But what really happened? Between 17 to 18, it was 1. But between 18 to 19, it has become 0. So is the input stable? No. again there is a violation. So here also there will be a violation. What violation would be there? Sir, here there is no setup violation, but hold violation is there. Now again output is unpredictable. Let's just say it has toggled. We don't know whether it will toggle or not. So just assuming that it has toggled, output will be actually unpredictable. It could be 1 as well, it would be 0 as well. So I am just assuming that it has toggled, but surely there is a violation. What violation is there? Hold violation is there. Hold violation is there. Now what about the next case? At 24 nanosecond, what is the input? 1. What it will do? Look back, look ahead. Look back for 3 nanosecond. So 24 minus 3. Let's make it 20, okay? Let's make it 20. Because at the edge, you never know that at the edge what will happen. So we try to avoid the edge condition. Okay, so we take the worst case. So let's go for 3 nanosecond back. 3 nanosecond back means 24 minus 3. That means 21 nanosecond. So this point will be 21 nanosecond. That means, yes, input is stable. And it should be stable for next 2 more nanosecond. That means for 2 more nanoseconds, that means 20 plus 4, 20 plus 2, 26. So it should be stable till this point as well. So 3 nanosecond back, 2 nanosecond ahead. That means it should be completely stable, which is stable as well. So there is no setup violation and there is no hold violation as well. Is the meaning of setup time, hold time clear to you? There is no setup violation, there is no hold violation. Why is that so? Because at the clock edge, the input is already stable and it is stable ahead as well. At the clock edge, stable, the input has been set up for 3 nanosecond, input will be stable for next 2 nanosecond as well. Right? So there is no setup or hold violation. What does that mean? Yes, here there will be perfect triggering. So perfect triggering will take place here. So here there will be perfect triggering. So this was the condition where there was no violation. This was also the condition where there is no violation, and we have understood the meaning of setup violation and hold violation as well. So here there was setup violation, here there is hold violation. So did you understand the meaning of setup time and hold time? Setup means input should be already stable. Hold means input should be stable for next hold time as well. Is that understandable to you? Setup time 3 nanosecond, that means when the clock edge is coming, input should be already stable for 3 nanosecond. Hold time 2 nanosecond, that means when the clock edge is coming, input should be stable for next 2 more nanosecond. Right? So this is the meaning of setup time and hold time. You just need to know the basic meaning. Now I will just tell you that how to solve the problems in the examination hall. So what kind of questions will be coming, how you will be dealing it, and how you will be solving it. That's the criteria now. So what they would be asking, they would give you this kind of circuitry, and they will ask you what is the maximum allowable clock frequency, or what should be the minimum clock time period to avoid setup violation. To avoid setup violation, what should be your time period of clock? And to avoid hold violation, what should be your minimum hold time? This is what they would be asking. What will be the question? To avoid the setup violation, what should be your minimum clock time period or maximum allowable frequency? We will see the gate PYQ, but this kind of question would be coming that you need to comment on T clock or T hold. So how will you comment on that? That we need to see. So our first target, first job, what would be the first job? We will see the input of the flip-flops. There is this flip-flop 1, I am calling this as flip-flop 1, and I am calling this as flip-flop 2. Now we will see which flip-flop is having fixed input. Is this having fixed input? Yes, sir. Input is fixed to 1. It could be 0 as well, or it could be 1 as well, but input is fixed. But this flip-flop is not having fixed input. So where there is not fixed input, let's just say here already the input was always 1. If input was always 1, will there be any setup violation, hold violation? No, because input is always stable. For at the clock edge, input will be stable before as well, it will be stable ahead as well. Input is always stable. Is that understandable to you? If the input was always 1. But here the input may be changing. It will depend on the output of this particular logic gate. Whatever it is, it could be any kind of circuitry. I don't know about this particular circuitry, but it will depend on the output of this particular circuitry. So here, what will be the scenario that we don't know? So this input is not stable. This input is not stable. Understandable? But this input is stable. Since this input is stable, I don't care about the setup time of this guy. Neither I care about the hold time of this guy. Is that understandable to you? So first we need to see that if the input is stable or not. Input is stable here. Job gone. Input is not stable here. Now this is my matter of concern. Now my target is that I need to reach to this point. In this circuitry, I need to start from the clock and I need to reach to this particular point. So from where it is coming? It is coming from the output of this guy. How the output of this guy is coming? Output of this guy is coming from this input. Now this input is coming from where? This input is coming from this Q. And from where this Q is coming? This Q is coming like this. Like if the clock edge would come, then some Q output would be there, that would be fed to this combination circuit, that will give some output, and then the input will be set up here. It could be either 0 or it could be 1. Is that understandable to you? First thing is that we need to see whether the input is fixed or not. If it is fixed, no need to worry about it. Only thing I need to worry about this guy. Now from where it is coming? So we will start from the clock, then I will have to go to this delay TD1, then I will have to go to this delay which is TD5, then I will have to go to this delay which is TD3. So this input will be stable after how much of delay? TD1 plus TD5. I don't care about the setup time of this, right? TD1 plus TD5 plus TD3. So this input will be stable after TD1 plus TD5 plus TD3 seconds or nanosecond, whatever it is. So to avoid the setup violation, this will be my clock equation, that T clock should be greater than or equal to. Sir, how this came? What is the logic behind that? That you can study in the comprehensive course by the timing diagrams. But here I need to just give the problem solving approach. So I'm just giving the problem solving approach, that how you need to start. You need to see that this input is not fixed. So I need to care about this input. From where it is coming, this is how it is coming. So TD1 plus TD5 plus TD3. TD1 plus TD5 plus TD3. So now I have started from the clock and I have reached here. Now what I will do? I will ask about the setup time to this particular flow. I have reached here. Now what I will do? I will talk to this flow and I will ask him, what is your setup time? He will say my setup time is TSU2. So I will add up that setup time as well. TSU2. Okay, is that clear to you? How did we start? Let me just make the diagram. How did we start? We started from here, clock, TD1. Why I am caring about this guy? Because the input is not stable here. So TD1, then delay of this guy TD5, then delay of this guy TD3, and then I have come here. Now just as I have come here, I will talk to this guy. What is your setup time? He will say T setup 2. I will add up this setup time as well. Minus of what? Minus the time which is taken by the clock to reach here. So this is your clock. After how much time the clock will reach here? The clock will reach here after TD2 time. The clock will reach here after TD2 time. That means I will subtract TD2 time from here. That's it. This is the T clock equation. This is your complete STA done. Your STA is done. Static timing analysis is done just by this equation. That's it. This is the job you need to do. And this kind of questions are asked in the GATE examination. That's it. T clock should be greater than. What we need to do is that, is this input fixed? No, it is not fixed. That means I need to come to this particular input that is coming from here. This is coming from here. So with the time you will build up the practice that I need to start from the clock. TD1 plus TD5 plus TD3. The input is fixed. Then I need to go to this guy. I need to ask its setup time. That will be T setup 2 minus T setup 2 plus T setup 2 minus something what? So this is the diagram that you can make. That go here, ask the setup time and then subtract it from here. Ask the setup time, add the setup time, and then see that when this guy is reaching. So here the clock is reaching after a delay of TD2. So subtract TD2 from here. That's it. This is the T clock equation. In the examination, they don't ask the whole equation, but you can write down the whole equation very easily. That's our whole time of second flow. Whole time of second flow. Whole time of this second flow. So what they would say, to avoid the hold violation. To avoid the hold violation. For avoiding hold violation. Hold violation. Now hold violation can occur in which flow? Hold violation can occur in which flow? Can it occur in here? No, because input is fixed. So it can occur only here only, no? So that equation would be that hold time should be less than or equals to, it should be less than or equals to what? Same equation, just remove this setup time. That's it. So same thing, that's why I need to reach till this point. Now I will not ask the setup time, I will simply subtract this delay. That's it. So what I will do? Sir, first TD1 delay I need to go, then TD5 delay I need to go, then sir TD3 delay I need to go. Not now I have reached here, I will not ask for the setup time, I will simply subtract this delay. That's it. This is the equation. TD1, TD5, TD3, TD setup to all these values will be given. Your answer would be achieved. That's it. So here the scenario was that this input was not fixed, but this was fixed. But now let's consider this particular scenario. Is this input fixed? No. It is coming from some combinational circuit. Is this input fixed? Have I written 0 here or 1 here? No, input is not fixed. No. From where it is coming? It is coming from the output of this combination circuit. Is that understandable to you? Right? So here this input is also not fixed and this input is also not fixed. This time both of the inputs are not fixed. So let's just call this as flip flop 1 and this as flip flop 2. So now the scenario is, in this particular scenario, this input was fixed. So we were working from flip flop 1 to flip flop 2. Can you come back from flip flop 2 to flip flop 1 here? No, because there is no path. But here there are two paths. Flip flop 1 to flip flop 2 as well and flip flop 2 to flip flop 1 as well. Again, it is very easy, just have some patience. This input is not fixed. From where it is coming? It is coming from here. From where this is coming from here. So what I will do, I will have to write down two equations now. What I will have to do, I will have to write down two equations now. What will be those equations? For avoiding setup violation. For avoiding setup violation. The scenario would be that, sir, your T clock should be, first I am working from flip flop 1 to flip flop 2 because this input is not fixed. So you need to work from flip flop 1 to flip flop 2. So first I am working from flip flop 1 to flip flop 2. So let's see how will I work. Starting from here, clock will see the delay of TD1, TD5. Look, this TD1 plus TD5, this is known as clock to Q delay. Okay, in the examination it might happen that this delay is not given. This delay is not given. So the name of this particular delay, TD5, what is the name of this particular delay? This is known as clock to Q delay. Clock to Q delay. Okay, clock to Q delay. So the name of this TD5 is clock to Q delay. Okay, so this language could be written in the examination, clock to Q delay. Or they can simply write down delay of flip flop. Delay of flip flop. Anything could be written, it should be clear to you. Okay, clock to Q delay or delay of flip flop, whatever could be written. So to reach till this point, how much delay you need to cover? TD1 plus TD5 plus TD3. So T clock should be greater than or equals to, first I need to cover TD1 plus TD5 plus TD3 plus TD5 plus TD3. So where I have reached? Here I have reached. Plus I need to go and ask him the setup time plus setup time of flop 2 minus. I will see that, sir, yes, I am here, but after how much time the clock is coming? Clock is coming after a delay of TD2. So clock is coming after a delay of TD2. So simply subtract that clock delay. That clock delay you need to subtract. That's it. So this is the clock equation you have written. What will be your whole equation? Sir, whole equation of flop 2, because we are moving from flop 1 to flop 2. So now whole equation of flop 2, that whole time of flop 2 should be less than or equals to, TD1 plus TD5 plus TD3, this guy is gone, minus TD2. That's it. Now this is the one scenario we have done. Another scenario is that this input is not fixed. From where it is coming? It is coming from here. From where this is coming? This is coming from here. From where this is coming? This is coming from here. From where this is coming? This is coming from here. That means what I will do now, I will work from here to here. Till this point I will reach, and once I have reached here, what I will say, what is your setup time? He will say my setup time is T setup 1. Then I will add up that setup 1. Then I will say after how much time the clock is reaching to you. He will say TD1. Then I will subtract it. So can you write down the equation on your own? Surely you can write down the equation on your own. Try writing it down on your own. What we need to do? We need to work TD2 plus TD6 plus TD4. Then I have reached here. Then add the setup time TSU1. Subtract this guy TD1. That's it. Okay. So the equation is that now we are working from flop 2 to flop 1. So your T clock should be greater than or equals to, start, TD2 plus TD6 plus TD4. TD2 plus TD6 plus TD4. TD2 plus TD6 plus TD4 plus T setup 1 plus T setup 1. Okay, I have reached here. I have asked the setup time as well. Now I will ask him that clock is reaching you after how much time? Clock is reaching me after TD1 time. So minus TD1. Understandable? So this is the T clock equation we have written. If I need to write down the whole equation of flip-flop 1, because now I have come to flip-flop 1 now. So the whole time should be less than or equals to what? Whole time of 1 should be less than or equals to TD2 plus TD6 plus TD4. Just I need to over the setup time minus TD1. That's it. So these are the equations I have written. Let's just say when I solved this equation, my answer came that T clock should be greater than or equals to 13 nanosecond, and this came that T hold should be less than or equals to 7 nanosecond. And when I solved this one, it came that T clock should be greater than or equals to 11 nanosecond, and T H1 should be less than or equals to 5 nanosecond. So these answers are certain that whole time of flop 1 should be less than 5 nanosecond. Whole time of flop 2 should be less than 7 nanosecond. Now the question would be that, sir, eventually what kind of clock you need to pick? Let's just say this is my clock. So what should be the time T clock here? What should be the T clock here? So what will be your answer? One guy is saying that it should be greater than 13 nanosecond. One guy is saying that it should be greater than 11 nanosecond. So what should be the answer? Sir, I will be happy if Virat scores 90 runs. If Virat Kohli scores more than 90 runs. And my friend will be happy if Virat Kohli scores more than 95 runs. That means how much runs Virat need to score so that both of you will be happy? More than 95. So T clock should be greater than 11. T clock should be greater than 13. So eventually I will say that my T clock should be greater than 13 nanosecond. If T clock is greater than 13 nanosecond, he is also happy and he is also happy. Is that understandable too? So you will solve the equations, whichever is the highest, that you will pick. Is that understandable or not? Surely it is understandable. Okay. So this is how we need to write down the equations. Let's see the GATE PYQ which came in 2015. You will be able to solve very easily. Again, like this was the question that was asked. So this input is not fixed, no? This X is not fixed. If this is not fixed, this is already not fixed, so this will also not be fixed. If this is not fixed, then this is also not fixed. Then this is also not fixed. Are you able to understand this point? This is already not fixed because it is coming from the output directly here. Already not fixed. Do you know the output? No. Right? So this is already not fixed. Let's just say this is your flop 1 and this is your flop 2. So input of flop 1 is already not fixed. What about the input of flop? Input of flop 2 is already not fixed. What about the input of flop 1? So input of flop 1 is coming from here. Is this output fixed? No. Why is that so? Because you don't know the value of X, no? If X was 0, then you surely know that, sir, this output will be surely 0. And if this output is surely 0, then this will be surely 0. And if this is surely 0, that means this input is surely fixed. That's for sure. But always when these delay based problems are coming, what I'm saying, always when delay based problems are coming, you always design for the worst case. And what is the worst case? The worst case is that X value you do not know. That means this value also you don't know. This value also you don't know. So solving this particular problem was not difficult in the examination, but I can make it difficult if I make two cases, that X equals to 1, X equals to 0. So we will talk about these two cases later on, but let's solve this problem first, that how I would be solving in the examination hall. So again, I could see that, sir, two flops are there, flop 1 and flop 2. Sir, clock to Q delay would have been given. Delay of AND gate is 1 nanosecond. Delay of this gate is 1 nanosecond. Positive has triggered. Setup time of 2 nanosecond. Setup time of 2 nanosecond is there. Whole time is 0 nanosecond. We don't care about it. And clock to Q delay is 2 nanosecond. So this is delay is 2 nanosecond. This delay is also 2 nanosecond. Now I know that, sir, this input is also not fixed and this input is also not fixed. Both the inputs are not fixed. Right? What does that mean? That, sir, I need to go from flop 1 to flop 2 as well and flop 2 to flop 1 as well. So let's work from flop 1 to flop 2. When I go from flop 1 to flop 2, what will happen? How will I work from flop 1 to flop 2? So, sir, clock to Q, 2 nanosecond. Then in between there is no combination circuit. Like when we were studying this particular topic, here there was some combination circuit which was having some delay, but here there is no delay. So started from here. How did we started? Started from here, 2 nanosecond delay, 2 nanosecond delay. I have reached here now. So first T clock should be greater than or equals to. So only I need to go through 2 nanosecond of delay. I have reached here. Now what I will do? I will ask him what is your setup time. He will say, sir, my setup time is. He will say my setup time is 2 nanosecond. So you will put 2 nanosecond there. Then I will say, after how much time the clock is reaching you? Then he will say that, yes, sir, clock is reaching me immediately. because there is no delay here, no? Like this is the worst case that I have picked. Like in the examination, this is the worst circuit that can come. In this particular circuitry, this guy is not even present. This is also not present. This is also not present. Only who is present? This is present. That's it. This is present. That's it. Right? I have taken the worst possible case delay. So whatever that is not present, that you will ignore. I will start from here, sir, 2 nanosecond of delay. Then I have reached here. I will ask him, what is your setup time? He will say 2 nanosecond. Then I will ask him, what is the time clock is taking? He will say, sir, 0 nanosecond. So I will subtract 0 nanosecond from here. So he is saying that T clock should be greater than 4 nanosecond. Is that the final answer? Absolutely not. Why is that so? Because I need to work from flope 2 to flope 1 as well. I need to work from flope 2 to flope 1 as well. So how will I work? So clock 2 till this point I will reach. How much time it will take? So T clock should be greater than or equals to clock 2 till this point. How much time it will take? 2 nanosecond. So this will take 2 nanosecond, right? Clock to Q, 2 nanosecond. Then after that, this is the combination circuit. Similar scenario. TD2 plus TD6, then this is the combination circuit, which is TD4. So 2 nanosecond, then another 1 nanosecond. So you will reach here after 3 nanosecond. So 2 nanosecond plus 1 nanosecond. So you will reach here after 3 nanosecond. Now you will stand here and you will ask him, what is your setup time? He will say, my setup time is 2 nanosecond. So you will add up that 2 nanosecond. Then you will ask him, after how much time the clock is coming? He will say, sir, after 0 nanosecond only. So subtract 0 nanosecond only. So T clock is coming out to be, should be greater than 5 nanosecond. So here the scenario was T clock should be greater than 4 nanosecond. Here the scenario is T clock should be greater than 5 nanosecond. So who you will listen to? You will listen to T clock should be greater than or equals to 5 nanosecond. So what is the minimum time period you can pick? What should be the minimum value of a time period? So that should be 5 nanosecond. So what should be the maximum value of a clock frequency? That would be 1 by 5 nanosecond. Okay. 1 by 5 nanosecond means this would be 1000. So 200 megahertz. This is the answer. So what will be the answer? 200 megahertz. Very straightforward question. Always work from where to where we need to go. Both of the inputs are not fixed. Job done. But what if in this problem x was 1? If x was 1, if one of the input of an AND gate is 1, can you surely tell what will be the output? No. It will depend on this particular guy. Are you able to understand this point? Like if input was 1, if x was 1, then again this output is unpredictable. It could be 1 as well, it could be 0 as well. I don't know about it. Right? If x was 1, then I don't know about this output. So same scenario would take place and answer would be, the same answer would be there, which will be 200 megahertz. But if x was 0, then what would have happened? If x was 0, so let's erase it all. If x was 0, if this x was 0, then this was fixed. If this was fixed, then this was also fixed. So you do not need to work from flope 2 to flope 1. You only need to go from flope 1 to flope 2. That's it. Then answer would have been different. It would be T clock should be, minimum T clock should be 4 nanosecond. Then answer would be 250 megahertz. So maximum allowable frequency would have been 250 megahertz. This question would be a brilliant question if they have put x equals to 0 here. If they have made x equals to 0, then what would have happened? If x equals to 0 here, this would also be 0, this would also be 0. That means this input is fixed now. So I don't care about the T clock or anything like that. I only care about this input now. Now when this input will be stable? This input is coming from here. Now from where it is coming? It is coming from here. So just go from clock to this particular input. How much time it would take? 2 nanosecond. So I am reaching here after 2 nanosecond. Just I have reached here, I will ask him what is your setup time. He will say 2 nanosecond. So I will add up 2 nanosecond. Then I will ask him how much time your clock is taking. He will say, sir, 0 nanosecond it is taking. So I will subtract 0 nanosecond. So my T clock would be greater than 4 nanosecond. A lot of people, what they would have done is that they would have surely worked from here to here. And a lot of people would have done it wrong. Okay, because they don't care about this thing that input is already stable. So always first thing you need to check is if the input is stable or not. Why is that so? Because in the gate examination, once the question I asked where the input was already stable. Okay, and now if they frame a good question on STA, they will surely make one thing that input will be stable. One of the input will be stable. Okay, so these are the things. Let's see more questions. Try solving this one on your own. This is also a gate PYQ only. This is also a gate PYQ only. Input of this flip-flop one. Is it stable? No. From where it is coming? Sir, it is coming from the output of this guy. It's not stable. right? What about input of this second flop? This is the input of the second flop. Is it stable? No, sir. From where it is coming? Sir, it is coming from the output of this guy. The output of this guy is coming from here, sir. It is coming from here. That means eventually it is coming from here. So did you understand the point? That both of the inputs are not stable. That means from flop 1 to flop 2 I will go, and flow from like this is the clock, and starting from here till this point I will go. So from flop 1 to flop 2, and then from flop 2 to flop 1 I will go. Just you need to work from flop 1 to flop 2, flop 2 to flop 1. Have some patience and start working. Flop 1 to flop 2. 1 to 2 I need to go. So this is my one. First I will see 3 nanosecond, then 2 nanosecond. First you see that if any of the input is stable or not. No, nothing is stable. Why is that so? Because this input is something that we don't know. So starting from here, first delay of 3 nanosecond. I don't care about the setup time whole time, only delay. 3 nanosecond, then delay of 2 nanosecond, then delay of 2 nanosecond. So this input has become stable after 3 plus 2 plus 2 nanosecond. So T clock should be greater than equals to, starting from here, 3 nanosecond plus 2 nanosecond plus 2 nanosecond. So this input is stable at 3 nanosecond plus 2 nanosecond plus 2 nanosecond. Then I will ask him, then I will come here, what is your setup time? He will say, sir, my setup time is 4 nanosecond. Then I will ask him, is there, how much time the clock is taking? So he will say that, sir, clock is coming immediately. And this guy will also say clock is already coming immediately. So nothing you need to subtract, 0 nanosecond you need to subtract. So what is the answer coming? The T clock should be greater than 3 plus 2, 5, 11 nanosecond. But is that the final answer? No. Why is that so? Because you need to work from flop 2 to flop 1 as well. So let's work from flop 2 to flop 1. So this is my flop 2 to flop 1. So this is the clock. Then it will see the delay of 8 nanosecond. 8 nanosecond and it will directly reach here. Flop 2 to flop 1. This is the clock. Came here. Then I see that it takes a delay of 8 nanosecond. So takes a delay of 8 nanosecond. So after the delay of 8 nanosecond, we have reached here. At this point, we have reached after a delay of 8 nanosecond. After a delay of 8 nanosecond. Then I will ask him, what is your setup time? He will say, sir, my setup time is 5 nanosecond. Then I will ask him, how much time your clock is taking? He will say 0 nanosecond. So what is the T clock we are getting? The T clock is greater than 13 nanosecond. So who I will listen to? I will listen to this guy. Right? Because he is saying greater than 11 nanosecond and he is saying greater than 13 nanosecond. So what will be your clock frequency? T clock minimum is 13 nanosecond. So T clock, F clock maximum would be 1 by 13 nanosecond, or in megahertz they are asking. So 1000 by 13 megahertz. Because nanosecond means 10 to the power 9. 10 to the power 9 means 1000 into 10 to the power 6. So 1000 divided by 13. 1000 divided by 13. What that would be? That you can see. 76.92. So 76.92 megahertz, that would be the answer. Is that understandable to you? Okay, so these are the gate questions that has been asked in recent years. Again, these kind of questions are framing, they are framing nowadays. But who knows what kind of question they can frame in future? So now we are seeing that what kind of questions could be coming in future. Okay. So this is the question that I gave in the test series. In our test series, I gave this particular question. Sir, it is looking like an easy question only. Right, sir? Why is that so? Sir, here I will reach, right? Starting from here I will reach, because I know that, sir, this input is stable. I don't need to care about it. This is flop 1. This is flop 2. Understandable? Right? So, sir, T clock should be greater than or equals to, sir, I will start from here. From where to where I will go? Flop 1 to flop 2. Why is that so? Because input of flop 1 is already stable. I don't care about it. I only care about this particular input. So I need to reach to this particular input. How much time it will take? So 2 nanosecond. What is the delay? Clock to Q delay is 3 nanosecond. Right? And setup time of both of them is 4 nanosecond, and buffer is having 2 nanosecond delay. So 2 nanosecond delay plus 3 nanosecond delay. First it will go through the delay of 2 nanosecond plus 3 nanosecond, then plus 2 nanosecond. So I have reached here now. 2 nanosecond plus 3 nanosecond, 2 nanosecond. I have reached here. Now I'll ask him, what is your setup time? What he will say, my setup time is 4 nanosecond. Then I will ask him, where your clock is coming. After how much delay your clock is coming. 99% of the students and a lot of teacher would also say 0 nanosecond, because here there is no buffer, no. 0 nanosecond. Right? So what will be the answer? So T clock should be greater than or equals to 11 nanosecond. That's it. This is wrong. Now in the gate examination, this kind of question only will come. All the question that we saw, positive was triggered, positive was triggered. Positive was triggered, positive was triggered. positive has triggered, positive has triggered. What is this? Positive has triggered, negative has triggered. Right? Now, what is the meaning of negative has triggered? Negative has triggered simply means that, like, this is simply an inverter, no? What is the meaning of inverter? What is the meaning of negative edge trigger? This is the meaning of positive edge trigger, right? That, sir, it will be triggering at positive edge. And what is the meaning of negative edge trigger? That it will be triggering at negative edge here. So, isn't it delayed by t clock by 2? Let's just say this particular window is t clock. So, it is triggering at t equals to 0, but this is triggering at t clock by 2. Or someone can say that, sir, this is triggering at t clock, but it is triggering at minus t clock by 2. That means this bubble will give the delay of plus minus t clock by 2. Although this bubble was not like this bubble was very small, we do not notice it. But actually from here to here when you are going, there is a delay of plus minus t clock by 2 involved. Plus minus t clock by 2 delay is already involved. Like basically if I want to make it positive as triggered only, I want to make this flow positive as triggered, what I need to do? I need to introduce a inverter here. What will happen now? Sir, this is positive as triggered, this will get this kind of a clock. Now, what this will get? Let's just say this bubble I have pulled out. If I have pulled out this bubble, so here clock is fed. Here what will be fed? Bar of the clock. So what will be the bar of the clock? Bar of the clock will be looking somewhat like this. Is that understandable to you? Now this bubble has been pulled out. What does that mean? It has become positively as triggered only. So what is the positive edge? This is the positive edge. Did you understand what did I do here? What I have done is that, sir, this was initially negatively as triggered. So what you used to do? That, sir, it will trigger at this particular point. Now what I did, I took out this bar. I took out this bubble. What I did, I took out that bubble and I made the clock somewhat like this. This is my clock now. Now clock is fed inverted. So this was your previous clock. Now the clock will be fed somewhat like this. Right? Inverted of this. 1 becomes 0, 0 becomes 1. Now this has become positively as triggered only because inverter I have taken out. This bubble I have taken out. So this has become positively as triggered. That means when it will be triggering? It will be triggering here only. So previously as well it was triggering at this point. Now as well it is triggering at this point only. So simply take out the bubble and that bubble, this inverter gives a delay of plus minus t clock by 2. It can give the delay of plus t clock by 2 as well. It can give the delay of minus t clock by 2 as well. Is that understandable to you? So one is positively as triggered, other one is negatively as triggered. So if I am saying that here there is 2 nanosecond of delay, so here also there is a delay of plus minus t clock by 2. So when I came here, I asked in the setup time is 4 nanoseconds. So till this particular point everything was fine. Till this point everything was fine. But when I asked him that what is your clock delay, that after how much time the clock is reaching you, then what he will say? He will say 0 nanosecond? No. He will say the clock is reaching me after plus minus t clock by 2 delay. Now it's up to you whether you will put plus t clock by 2 here or minus t clock by 2 here. Think about it. Whether I will put plus t clock by 2 or minus t clock by 2. You need to find out for the worst case. That worst case that t clock should be greater than or equals to this. That means there is some guy who is saying that Virat should score more than 80 runs. Some guy is saying that Virat should score more than 90 runs. Some guy is saying that Virat should score more than 100 runs. So Virat have to score 110 runs so that everyone would be happy. That means this value should be very large. Right? Now this value should be very large. That means this value has to be largest. Whatever the value that you are getting here, this value has to be largest. Say yes or no. T clock should be greater than the largest one. Some guy is saying 80 runs, 90 runs, 100 runs. That means Virat needs to score more than 100 runs. So what Virat will pick? Virat will pick the maximum target, that is 100 runs. So this value has to be largest. If you want this value to be largest, then whatever that is being subtracted, that has to be minimum or maximum. 3 minus something. I want this value to be largest. So will I subtract minus 1 from it or will I subtract plus 1 from it? I want this value to be largest. Something has to be subtracted. So will I subtract plus 1 or minus 1? I will subtract minus 1 because now the value will become 4. If I have subtracted 1 only, then the value would have become 2. That means you want this value to be largest, and if you want it to be largest, then what you will be subtracting? You will be subtracting the minimum value. So two kind of delay you are getting, either plus t clock by 2 or minus t clock by 2. So what value you will put here? Plus t clock by 2 or minus t clock by 2? You will put minus t clock by 2. There you go. Okay. So now what is the scenario? The equation has become t clock should be greater than or equals to, sir, started from here 2 nanosecond, 3 nanosecond, 2 nanosecond. Then I asked the setup time. So it became 11 nanosecond. Minus, I am having elaichi, okay, because I am having cough. So that's why I am having elaichi. Those who are my older students, they would know that I always have some elaichi in my mouth when I am recording the video, not pan masala. Okay, because we are not the fan of Ajay Devgan. Although I am from Rajasthan, doesn't mean that I will be having pan masala. Okay, don't think that all the Rajasthanis will have pan masala. Some Rajasthani may have tansin as well. Yeah. So what I was saying, this is minus. Yeah. So what I was saying that I need to subtract the minimum value, right? So what could be the minimum value? Either it could be plus t cube by 2 or it could be minus t cube by 2. So which one is the minimum? Minimum is minus t cube by 2. Why is that so, sir? Because this is negatively s triggered. And what is the meaning of negative s triggered? Meaning of negative s triggered is that this, yes sir, it is providing some delay. It is providing the delay of plus minus t clock by 2. I will pick minus t clock by 2. So this minus sign, it will become plus sign. Now this t clock by 2 goes here. So t clock minus t clock by 2, it will become t clock by 2. That should be greater than 22 nanosecond. So t clock should be greater than 22 nanosecond. That would be the correct answer. That means what should be the minimum clock period? That should be 22 nanosecond. Surely in future this kind of question is coming in your examination hall. Surely it is coming. Okay, this will be negatively triggered for sure. So what you need to do is that take out this bubble outside, and you will say that, sir, it is giving a delay of plus minus t clock by 2. So here I need to subtract the minimum value. So minimum delay would be minus t clock by 2. So that minus t clock by 2 you will put here. Is that understandable to you? Okay. We will see some more questions, some more scenario we will see. This particular question we need to see. Then we will see this question. With this question we will see, and then we will see this question. Then the video will end. And then last question. So I will take a break. Okay. Because I am a bit tired. So I will take a break. Then I will come back. We will deal these questions as well. Right. So yeah, let me take a break and then I will come back. Yeah, welcome back. So let's try this particular question. So here there are 3 flip-flops. Till this date in the gate examination, they did not put three flip-flops, but who knows, in the future they can put. So this is your flip-flop 1, flip-flop 2, and flip-flop 3. This input is not fixed because it is coming from a sequential circuit. This input is also not fixed, but this is fixed. So I don't care about flip-flop 1. I only care about flip-flop 2 and flip-flop 3. So from where this input is coming? Sorry, from where this input is coming? So it is coming from here, 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 and from here. So first I will work from flip-flop 1 to flip-flop 2. Then from where this is coming? So this is coming from here. And from where this is coming? This is coming from here. Is that understandable to you? Let me repeat it again. From here it is coming. From where this input is coming, this is coming from here. From where this guy is coming, this guy is coming from here. Like basically there is a path between flop 1 to flop 2. And similarly there is a path between flop 2 to flop 3. You cannot say, sir, I will work from flop 1 to flop 3. There is no direct path. If there was a connection like this, then you could have said that, yes sir, now I can work from flop 3 to flop 1. But direct path is there, that is flop 1 to flop 2 and flop 2 to flop 3. These are the direct path. Okay. So what all scenes we are having? Flop 1 to flop 2. T clock should be greater than 0 delay, then delay of flip-flop is 3 nanosecond. So 3 nanosecond plus 2 nanosecond. So I have reached here after 5 nanosecond. So 3 nanosecond plus 2 nanosecond. Then what I will ask him, what is your setup time? He will say my setup time is 1 nanosecond. Minus. Then I will ask him, after how much delay your clock is coming? So he will say, sir, after 1 nanosecond of delay, like here, after how much delay clock is coming? This is the clock. So it is coming after 1 nanosecond of delay. Just 1 second, guys. Just 1 second. Yeah. So after how much delay this clock is coming? After delay of 1 nanosecond it is coming. Right? So this clock is coming after a delay of 1 nanosecond. So 1 nanosecond you will subtract. So your T clock is greater than or equals to 5 nanosecond. You can write down the whole equation as well. What will be the whole equation? Hold of flip-flop 2. Hold of flip-flop 2 should be less than or equals to 3 nanosecond plus 2 nanosecond. Just this 1 nanosecond will not come. Setup time will not come. Minus 1 nanosecond. Same, just this particular thing will not come. So your hold time would be less than or equals to 4 nanosecond. So this is the answer of hold time. Okay, and this is your T clock. Now we need to work from flope 2 to flope 3, right? We will work from flope 2 to flope 3. Understandable? So we need to reach till this point. So we will start from the clock. There is a delay of 1 nanosecond. Then, like this delay will be counted. You are not starting from here. You will always start from the clock. So delay of 1 nanosecond. Then delay of a flope will be there. What is that? 3 nanoseconds. So 1 nanosecond plus 3 nanosecond, then plus 3 nanoseconds. So then you will reach till this point, right? So starting from here 1 nanosecond, then delay of a 3 nanosecond, then delay of 3 nanosecond. So T clock should be greater than equals to 1 nanosecond plus 3 nanosecond plus 3 nanosecond. So 1 nanosecond plus 3 nanosecond plus 3 nanosecond, right? So where I have reached? Here I have reached. Then I will ask him what is your setup time. He will say my setup time is 1 nanosecond. Now the interesting part would come. What you will be subtracting here? Think about it and tell me the correct answer. It should not be wrong. What you will be subtracting here? Will you be subtracting 4 nanosecond or something else? I will reach here. I have asked him the setup time. Now I will ask him after how much delay the clock is reaching you. So clock is here. So clock is reaching here after a delay of 1 nanosecond plus 4 nanosecond. That means clock is reaching after a delay of 5 nanosecond. This was the beauty of this question. That's it. This is the beauty. That clock is reaching here after a delay of 1 nanosecond plus 4 nanosecond. That means after a delay of 5 nanosecond. So here I will be subtracting 5 nanosecond. This is the most important part. A lot of people will be saying, sir, this is the skew. No. Clock is reaching here after how much time? 5 nanosecond. 1 plus 4. This is known as skew. Okay. This particular thing is known as skew. So skew of this particular clock is 5 nanosecond, not 4 nanosecond. Skew of this clock is 1 nanosecond. Skew of this clock is 0 nanosecond. There is no skew. That means clock is directly reaching here. Is that understandable to you? So this will be your 5 nanosecond here. So what is the answer you are getting here? T clock should be greater than or equals to 3 nanosecond. So hold time of third flope should be less than or equals to 1 nanosecond plus 3 nanosecond plus 3 nanosecond. Just this whole time will not come, minus 5 nanosecond. So whole time of third flope should be less than or equals to 2 nanosecond. Okay. So these are the scenarios. Now he is saying that it should be, let's not put it in the box. Did you understand how did I write down this particular equation? Which equation? This equation. That is pretty much understandable. Just this whole time will not come. That's it. Rest all is fine, right? So these are the two different answers. Now other answer will be coming from here. So he is saying greater than 5 nanosecond. He is saying greater than 3 nanosecond. So who you will be listening to? I will be listening to greater than 5 nanosecond. That means my F clock maximum could be 1 by 5 nanosecond. That could be 1000 by 5 megahertz. So answer would be 200 megahertz. This is the answer. Okay. Let's solve this question. All the inputs are fixed. 1 fixed, 1 fixed, 1 fixed. No meaning of setup time. Now I will give you this particular circuitry. Which of the following statements are correct? First one, there will be setup violation. Second option, there will be hold violation. Both of the options are incorrect. Why is that so? Because all the inputs are fixed. If inputs are fixed, then there is no meaning of setup violation or hold violation. No, like why this setup violation, hold violation came into action? Because inputs were not fixed. Input was changing. He is saying that input should be stable. It should be stable for hold time or setup time. They are already stable. That means there would be no setup violation or hold violation. So these kind of questions have you already seen? What kind of circuitry it is? It is your asynchronous down counter. Is it synchronous? No. Why is that so? Because clock is being fed from the previous output. So it is asynchronous. Asynchronous. Is it up counter or down counter? It is down counter. So it is asynchronous down counter. How did you remember? Positive, 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 positive will repel each other. That means goes down. Or if it was negative, negative, then also goes down. If negative, positive goes up. So it is asynchronous down counter. Asynchronous down counter. So let's just say initial states are 0, 0, 0. Initial states are 0, 0, 0. So it will down count. That means it will go to 7. Then it will go to 6. It will go to 6. And in that manner, it will keep on counting down. Right? and then it will again go back to 0. But there will be some condition on t clock for sure. Like such setup violation, hold violation will not be there, but t clock should be greater than or equals to a certain value. Why is that so? Let's draw the timing diagram. Like I hope you might have already seen this topic in your class notes, but if you haven't seen, then this kind of questions are also very important. They have already come in your gate examination. Okay, these kind of questions have already come in the gate examination. That's what will be the condition on t clock. So what that would be? So let's see by the timing diagram. Let's just say this is my clock, and initially I am saying that all the outputs are at 0. So let's just quickly let me draw these things. So initially I am saying that all the outputs are at 0. Initially all the outputs are at 0. Q0, Q1 and Q2 all are at 0. Q0, Q1, Q2 all are at 0. Now what will happen? All are in toggle mode, right? This is in toggle mode, this is also in toggle mode, this is also in toggle mode. So what will happen now? Just as the clock is fed, what will be the instruction? Instruction will be that you need to toggle now. So what this Q0 will get the instruction that you need to toggle now. He will say that, sir, yes, I will toggle, but I need a delay of 2 nanosecond. So yes, sir, I will go from 0 to 1, but after a delay of 2 nanosecond. Say yes or no. This is what he will say. Did you understand this point or not? That yes, sir, I will go from 0 to 1, but after a delay of 2 nanosecond. Then again he will toggle here. Again the process will keep on going, but let's analyze for first cycle only. So now this is the positive edge. So this Q0 is being fed. This Q0 is being fed as a clock here. This Q0 is being fed as a clock here. So at this particular time, at 2 nanosecond, let's just say this was t equals to 0 nanosecond. So at 2 nanosecond, this flow has got the instruction that you need to toggle now. At 2 nanosecond, the positive has come. The positive edge has come. The positive edge has come. So this flow has got the instruction that you need to toggle now. So he will say, yes, sir, I will toggle, but after a delay of 1 nanosecond. So what will happen is that till this particular point, there was no toggling. Here he got the instruction that you need to toggle. He will say, yes, I will toggle, but after a delay of 1 more nanosecond. So here he will toggle now. So after a delay of 1 more nanosecond. Right? Now again, this is fed as a clock. Positive edge has come. So at this particular time, he will get an instruction that you need to toggle. So he will say, Q2 will say, yes, sir, I will toggle, but after a delay of 4 nanosecond. So he will say, yes, I will toggle, but after a delay of 4 nanosecond. After a delay of 4 nanosecond. So 2 nanosecond, 1 nanosecond, after a delay of 4 nanosecond. Then your desired output, which was 1, 1, 1. Look, this is the desired output, no? From 0, 0, 0, you expected the output to be 1, 1, 1. But here you are getting the output 0, 0, 0 only. Then you are getting the output to be 1, 0, 0. Although it is like this is your LSB, right? This is your LSB. So we should read 0, 0, 0, 0, 0, 0, 0, 0, 1. Then I am getting the output to be 0, 1, 1, which is not the desirable output. Desirable output is 1, 1, 1. So I need to get this particular output. Now let's just say if this delay was very much higher. Let's just say this delay was 10 nanosecond. So he will be toggling somewhere here. Then you will be never achieving this 1, 1, 1 output. Are you able to understand this point? That means whatever this total delay is there, how much was the total delay? First one was saying 2 nanosecond delay, then 1 nanosecond delay, then 4 nanosecond delay. So total delay is 7 nanosecond. So this 7 nanosecond delay should be covered in 1 clock cycle or in 1 clock period. If this delay is not covered in 1 clock period, then there is a problem. This will become 1, but after some time, after very huge time, right? Like let's just say this 4 nanosecond was, let's just say this t clock is 8 nanosecond. And in place of 4 nanosecond, it was 10 nanosecond. So he will say, yes, I will toggle here, but after 10 nanosecond, somewhere here he will be toggling. So what you will be receiving 1, 1, 0 only, which is not desirable. You want to achieve 1, 1, 1. That means all the toggling should take place in one time clock only, in one time period only. What does that mean? That means your t clock should be greater than or equals to 7 nanosecond. That means at least this much should be achieved. Otherwise, you will never be able to get 1, 1, 1. Is that understandable to you? So usually people remember it. What people remember it? What people remember? They remember that in case of asynchronous counter, you need to add up all the delays. And in case of synchronous counter, you need to pick up the maximum delay. But this is the reasoning. I just wanted to give you the reasoning here as well. Right? So in case of asynchronous counter, this is being fed as a clock, this is being fed as a clock. So what is happening? This is toggling. He will say I will toggle after 1 nanosecond. He will say I will toggle after 4 nanosecond. So whatever the toggling process, that should happen in one clock period only. But what is the case of synchronous counter? In synchronous counter, all are fed with the same clock. So at t equals to 0 only, just as the positive has come, just as this positive positive edge has arrived, everyone has got the instruction that you guys need to toggle. Just as this positive edge has arrived, everyone is getting the instruction that you guys need to toggle now. So Q0 will say, initially I am 0, initially I am also 0, initially I am also 0. Q0 will say, yes sir, I will toggle, but this is the output. So Q0 will say that, sir, yes sir, I will toggle, but I need a delay of 2 nanoseconds. So I will toggle after 2 nanoseconds. So here everyone got the instruction, here everyone got the instruction that start toggling. He will say that I will toggle after 2 nanoseconds. What the next guy will say? Sir, I will toggle, but after a delay of 1 nanosecond. So he will be toggling after 1 nanosecond. And what the next guy will say? That's yes sir, I will toggle, but after a delay of 4 nanoseconds. Two nanosecond, 1 nanosecond, and 4 nanosecond. Now, if you want to achieve the next state, which is 1111, that means all the toggling should take place in one cycle only. So, what is the maximum time? Like this toggling has already taken place, this toggling also has already taken place. This is taking place in the last. What does that mean? That means t clock should be greater than this 4 nanosecond, greater than or equals to 4 nanosecond. So in case of synchronous counter, this is the condition, that your t clock should be greater than or equals to 4 nanosecond. So this is the difference between synchronous and asynchronous. Usually people remember it, that if the question is coming on asynchronous, just add up all the delays. T clock should be greater than or equals to addition of all of them, TD1 plus TD2 plus TD3 in case of asynchronous. But in case of synchronous, what people will say, the t clock should be greater than or equals to maximum of TD1, TD2 and TD3. Eventually you can remember it, but now you have got the reasoning as well. Similarly, if you need the reasoning of all these equations, that's how we are writing down all these equations, then study from a good resource in comprehensive course. Okay, and if you only want the reasoning of a STA, then this video has been already made. Okay, you can watch from here. But as of now, I cannot give the complete explanation of STA, right? It is not feasible for me. It will take a lot of time, right? But you are getting good enough problem solving skills. If the question is coming on delay, which is actually a rank deciding question, not everyone would be attempting those questions, but you will be able to attempt it for sure if you just watch this particular video. Let's go to the next question, which is a gate examination question and one of the best question of complete digital electronics. Maximum allowable frequency. Maximum allowable frequency, what does that mean? They are asking t clock should be greater than or equals to what, or you can say f clock should be less than or equals to what. So this is something I need to find out. T clock should be greater than or equals to what. Sir, setup time is given, delay is given, all these things are given. Where is the issue? Issue is there only at this guy. Why is that so? Input fixed. Input fixed. No issue. The only problem is here, that when this input will be stable. From where this input is coming? This input is coming from here. From where this guy is coming? This guy is coming from here. Now from where these two guys are coming? He is coming from here, and from where this will come? This will come from this particular clock. Right? From where this input will come? This input will come from this particular clock. And from where this input will come? This input will come from this particular clock. Is that understandable to you? Like first I will see that when these guys will be stable. Once I get to know that when these guys will be stable, I will be able to know that when this will be stable. Is that understandable to you or not? What I am saying? I need to know that when this S will be stable. If I am able to know when this S will be stable, then what I will say? That my t clock should be greater than or equals to, let's just say this is stable at TD nanosecond. So I will say t clock should be greater than TD. Then I will ask him what is your setup time. He will say my setup time is 5 nanosecond. Then I will ask him after how much time the clock is coming. He will say 0 nanosecond. So this will be your answer. That's it. So you need to know that when this will be stable. This will be stable when these two guys are stable. And now when these two guys are stable, that is your matter of concern now. So when this output will be stable, what do you think? Starting from here, clock, then he will see the delay of 15 nanoseconds. So this output will be stable after 15 nanoseconds. Previously we used to say that this output will be stable after 15 nanoseconds. This is simply Q, this is Q bar. So this will be this will be stable after 15 nanosecond. So this will also be stable after 15 nanosecond. Now the same 15 nanosecond will be fed here as well. That means this input is stable after 15 nanosecond. Is that understandable to you? Now this clock is stable after 15 nanosecond. This clock is stable after 15 nanosecond. So how much time, after how much time the output will be stable? Let's go to this scenario. This clock was stable after 2 nanosecond. This output was fed as a clock, which was stable after 2 nanosecond. So this output was stable after how much time? 2 nanosecond plus the delay of it. 2 nanosecond plus the delay of himself. So similarly, this clock is stable after 15 nanosecond. So after how much time this output will be stable? If this output is stable, that means this output is also stable, because this is Q, this is Q bar. So clock is stable after 15 nanosecond. So 15 plus 15, this output will be stable after 30 nanosecond. That means this output will also be stable after 30 nanosecond. So what does that mean? Here, both of the inputs of this AND gate will be stable after 30 nanosecond. Did you understand how we are approaching the problem? Again, best question of digital electronics, one of the best question. Best question, I would say that FSM question, which came in 2018 from IIT Guwahati only. Okay, that was based on which question it was? That was based on sequence detector. Or some people will say that it is based on finite state machine, but actually it is not based on finite state machine. So, so that is the best question of digital electronics. This will be the second best question. So here what is the scenario is that we need to find that when this input will be stable. So this input will be stable when these two inputs are stable. This input will be stable when this guy is stable. When this guy will be stable, that starting from here, 15 nanosecond time it will take, so it will be stable here. Now the same guy will be stable after 15 nanosecond. This is being fed as a clock, so it takes 15 nanosecond plus 15 nanosecond. This will be stable after 30 nanosecond. So this is an AND gate. He is stable after 15 nanosecond. Now he is waiting for him. That now you have become stable. Yes sir, I have become stable. Now this final output will be stable. So after 30 nanosecond, they will start giving the output. Like he says that, sir, I am stable at 15 nanosecond, but he have to wait for this guy, no? 15 nanosecond guy will have to wait for this guy. So they will start giving the output after 30 nanosecond, but gate will say that I am also having a delay of 5 nanosecond. That means output of this gate will be stable at 35 nanosecond. What does that mean? That means this particular input will be stable at 35 nanosecond. Started from here, 15 nanosecond, stable. 15 nanosecond plus 15 nanosecond, 30 nanosecond. So this gate will say that 30 plus 5, after 35 nanosecond I will be stable. So this input is stable at 35 nanosecond. Now you already know that if this is stable at 35 nanosecond, you will simply ask him what is your setup time minus how much time the clock is taking, 0 nanosecond, your job is done. So your T clock should be greater than or equal to 35 plus 5, 40 nanosecond. That's it. Okay, and if you need to find out the clock frequency, then what you need to do? Simply 1 by 40 nano, or you can say 1000 by 40 nano. So it will become 250 mega. Not 250. 25 megahertz. It will become 25 megahertz. Okay, so F clock will become 25 megahertz. Understandable? Right? So maximum allowable frequency is 25 megahertz. That would be the answer. Again, very good question. I hope you have understood it. We just need to check that when our output being stable. Starting from here, and that's it. So always check that which guy is not stable. Just go to him, then ask him that when you will be stable. Just keep on looking that from where they are coming, and just keep on working in the circuitry. That's it. Okay. This is the last one. Try thinking about it. Only one flop is there. Is the input of the flow fixed? No, it is not fixed. From where it is coming? It is coming from here. From where this guy is coming? It is coming from here. From where he is coming? It is coming from here. Right? And from where it will come? It will come from the clock. So what should be your T clock? So T clock should be greater than or equal to. So first it will have to go through this TD1 delay. TD1 delay plus the delay of this flow. What that would be? 3 nanosecond. Then I have reached here. Then I need to reach here. Starting from here, going here, then I will see the delay of 2 nanosecond plus 2 nanosecond. Then again, I will reach here. Now, once I have reached here, what I will say? What is your setup time? He will say my setup time is 1 nanosecond. Then I will ask him after how much delay the clock is coming. He will say, sir, the clock is coming after TD1 delay. So minus TD1. This TD1 and TD1 is getting cancelled. Your T clock is greater than or equal to 6 nanosecond. That's it. This is also a future question. Surely in future this could be coming. Okay, this is also a future question. This is already a very good question. Came in 2004. Then it is more appreciated because at that time there was not much concepts evolved, right? Like there was no a lot of textbook, or like whoever framed this question, really he should be appreciable. That professor should be really appreciable. So this was already a good question. This is also something that will be coming. Okay, these kind of questions have already come. These kind of questions have already come. This is also a future question. This is also a future question, and this is also a future question. Okay, and this kind of question have already come. So 3 kind of future question we have seen, and all the PYQs we have seen, right? I know that future concept is not very straightforward, but enough reasoning and enough explanation I have given. Now I hope you are comfortable. And this kind of question is also like looks like a very small question, but very easy it is, right? Starting from TD1, I know that input is not fixed. From where it is coming? Coming from here. From where? Here. Here. Starting from here, TD1 plus delay, then you reach here, ask him the setup time, then ask him after how much time the clock is coming, minus TD1. Both get cancelled out. T clock should be greater than or equal to 6 nanosecond. So here your delay based problem or static timing analysis problem will be ending. Okay. Now you can watch this video. Last year question came from here. I uploaded this video 1 year back only in October, November, because I knew that in 2025, before GATE 2025, I knew that this question is coming. That's why I uploaded it on YouTube. Okay. Because in previous years, from a lot of time, the question did not come from static timing analysis. So it was surely coming. It was already like expected that question would be coming. This year, I am expecting that question would be coming from FSM. Like 5 star I am putting. 5 star. That surely the question could be coming from FSM. And the FSM that we study, we only study in a very surface level. I hope you want to study in a much in-depth manner. So please study from here. The question might be coming on FSM. And a very good question might be coming. Already video has been already uploaded. 8 months back I have uploaded the video. You can see the number of views as well. A lot of people are already watching. You should also watch it. Okay. Just type FSM by Himanshu Agrawal. Very high chances that question are coming from here. If you have studied digital electronics, you should surely study FSM as well. And again, a different point of view is there. And that GATE 2018 question, that also we have solved here. That question also have been solved here. Well and good. Okay. So yeah, with that, I will be ending this video. So within 70 to 75 minutes, we have understood the complete concept of delay based problems. Okay. Yeah. Thank you very much. Happy learning.